energy crisis in the 70s and onward changed the approach and priorities in the field of discovery of new conventional energy resources. It enhanced the efforts by various countries to look for alternate indigenous and renewable energy resources. In the process, wind energy, solar energy, geothermal energy and sea wave energies were tried and developed as non-conventional energy resources in various countries depending upon their requirements. The energy demand is increasing with the economic growth and rise in population. Due to the use of fossil fuels, the amount of greenhouse gases emitted into the atmosphere is increasing considerably, which results in negative impact on climate and hence on the human life. Climate change is a real threat to our future, and a major cause is the use of fossil fuels to power homes and business. So, the use of fossil fuels must be reduced as a source of energy. This challenge forced the researchers and scientists to exploit some renewable energy resources which are friendly environmentally and economically as well. One of the renewable energy sources is also geothermal energy, whose exploitation is becoming more and more competitive as the prices of fossil fuels rise. The benefits of using geothermal energy as an alternative resource are extremely large. A systematic geothermal survey in India began in 1973, undertaken by Geological Survey of India, and the existence of 340 potential sites was reported. 11 geothermal prospective districts have been identified till date. In this section, we will be discussing about the following aspects of geothermal energy: geothermal energy and its origin, geothermal systems in India, potential of geothermal resources in India, prospects of geothermal energy in India, advantages and disadvantages of geothermal energy. Geothermal energy and its origin. The word geothermal originates from the Greek roots geo meaning earth and thermos meaning heat. Geothermal energy is thermal energy generated and stored in the earth. Earth geothermal energy originates from the original formation of the planet, from radioactive decay of minerals, from volcanic activity, and from solar energy absorbed at the Earth's surface. The geothermal gradient, which is the difference in temperature between the core of planet and its surface, drives a continuous conduction of thermal energy in the form of heat from the core to the surface. About 400 thermal springs are known to occur in India, falling in orogenic, that is the Himalayan, as well as non-orogenic, that is peninsular province. 31 areas have been examined in detail, and finally shallow drilling has been done in 16 areas. The temperatures of these springs range from 35 degrees Celsius to the boiling point of water. Although volcanic eruptions contain small portions of the molten rock that feeds them, the vast containing hot water, water and steam or steam at depths of 500 meters to greater than 3000 meters. There are 4 major types of geothermal energy resources. 1. Hydrothermal. 2. Geopressurized brines. 3. Hot dry rocks. 4. Magma. How is geothermal energy captured? The technology. Normally, geothermal energy is captured from geothermal hotspots. Basically, a hotspot is an area of reduced thickness in the mantle which allows the excess internal heat from the interior of the earth to flow to the outer crust. These hotspots include the volcanic islands, mineral deposits and geysers, normally known as hot springs. Mile or more deep wells can be drilled into underground reservoirs to tap steam and very hot water that drive turbines that drive electricity generators. 4 types of power plants are operating today. First, flashed steam plant. The most common way of capturing energy from geothermal heat is to tap into naturally occurring hydrothermal convection systems where cooler water seeping into Earth's crust is heated up and it then rises to the surface. When heated water from the hot springs is forced to the surface, it is a relatively simple matter to capture that steam and use it to drive electric generators. In order to set up geothermal power plants, holes are drilled into the rock to capture steam more effectively to drive electric generators. If the water comes out of the hot spring as steam, it can be used directly, whereas the hot water can be used as a flash system. The steam gets condensed and is converted into water again, which is returned to the reservoir. Flashed steam plants are widely distributed throughout the world. Second, dry steam plant. Usually, geysers are the main source of dry steam. Those geothermal reservoirs, which mostly produce steam and little water, are used in electricity production systems. As steam from the reservoir shoots out, it is used to rotate a turbine after sending the steam through a rock catcher. The rock catcher protects the turbine from rocks which come along with the steam. Third, binary power plant. In this type of power plant, the geothermal water is passed through a heat exchanger where its heat is transferred to a secondary liquid, namely isobutene, isopentane or ammonia water mixture present in an adjacent separate pipe. Due to this double liquid heat exchanger system, it is called a binary power plant. The secondary liquid, which is also called as working fluid, should have lower boiling point than water. It turns into vapor on getting required heat from the hot water. The vapor from the working fluid is used to rotate turbines. The binary system is therefore useful in geothermal reservoirs which are relatively low in temperature gradient. Since the system is a completely closed one, there is minimum chance of heat loss. Hot water is immediately recycled back into the reservoir. The working fluid is also condensed back to the liquid and used over and over again. Fourth, hybrid power plant. Some geothermal fields produce boiling water as well as steam, which are also used in power generation. In this system of power generation, the flashed and binary systems are combined to make use of both steam and hot water. Efficiency of hybrid power plants is, however, less than that of the dry steam plants. Enhanced geothermal system and location of such natural reservoirs. EGS reduces these constraints by allowing for the creation of hydrothermal reservoirs in deep, hot, but naturally dry geological formations. EGS techniques can also extend the lifespan of naturally occurring hydrothermal resources. Given the costs and limited full-scale system research to date, EGS remains in its infancy with only a few research and pilot projects existing around the world and no commercial scale EGS plans to date. The technology is so promising, however, that a number of studies have found that EGS could quickly become widespread. On the basis of enthalpy characteristics, the geothermal systems in India can be classified into medium enthalpy, 100 degrees Celsius to 200 degrees Celsius, and low enthalpy, lesser than 100 degrees Celsius geothermal systems. These are described as follows. Medium enthalpy geothermal energy systems. The medium enthalpy geothermal energy resources are associated with 1. Younger intrusive granites as in Himalayas, that is Puga Chumathang, Parbati, Beas and Sutlej Valley geothermal fields. 2. Major tectonic features or lineaments such as the west coast areas of Maharashtra, along the Son Narmada Tapi lineament zone at Salbardi, Tapi, Satpura areas in Maharashtra, Tattapani in Chhattisgarh and Rajgir Mungyar in Bihar, Tatta and Jaram in Jharkhand, and Eastern Ghat tracts of Orissa. 3. Rift and grabens of Gondwana basins of Damodar, Godavari and Mahanadi valleys. 4. Quaternary and tertiary sediments occurring in a graben in the Cambay basin of West Coast. Low enthalpy geothermal energy systems. The low enthalpy geothermal energy systems are associated with 1. Tertiary tectonism and neotectonic activity. 2. Shield areas with localized abnormal heat flow which is normally very low. Geothermal provinces in India. Physiographical India is divisible into 3 distinct geographical units, that is, the extra-peninsular region, Indo-Gangetic plain and the peninsular region. A variety of rocks ranging in age from Archean to Holocene are exposed in these geographical units. The thermal springs have been classified on the basis of their occurrence in specific geotectonic setups and have been grouped under different geothermal provinces. The geological and structural criteria that have been used in the identification of the prospective geothermal provinces are occurrence in an orogenic belt which has undergone Cenozoic folding and upliftment, occurrence in structural depressions or grabens associated with late tertiary and quaternary upliftment in non-orogenic belts, related to deep fault zones associated with recent seismicity, occurrence in the areas of tertiary or quaternary volcanic activity. Uses of geothermal energy. In fact, geothermal energy is one of the oldest natural resources of heat and dates back to the Roman times when the heat from the earth was used instead of fire to heat rooms and or to warm water for baths. Presently, it is being used as a source for producing electricity mainly along plate margins. The general characteristics of geothermal energy that make it of significant importance for both electricity production and direct use include extensive global distribution. It is accessible to both developed and developing countries. Environmentally friendly nature. It has low emission of sulfur, carbon dioxide and other greenhouse gases. Indigenous nature. It is independent of external supply and demand effects and fluctuations in exchange rates. Independence of weather and season. Contribution to the development of diversified power sources. Geothermal energy can be used very effectively in both on and off-grid developments and is especially useful in rural electrification schemes. Its use spans a large range from power generation to direct heat uses, the latter possible using both low temperature resources and cascade methods. Cascade methods utilize the hot water remaining from higher temperature applications, example, electricity generation, in successively lower temperature processes, which may include binary systems to generate further power and direct heat uses, bathing and swimming, space heating, including district heating, greenhouse and open ground heating, industrial process heat, aquaculture pond and raceway heating, agricultural drying, etc. Potential of geothermal resources in India. The Geological Survey of India estimated the geothermal potential of the country to be of the order of 10,000 megawatts based on the existing boreholes in some of the geothermal provinces like Pyuga, Chumathang, Manikaran in Himalayas, and Tattapani and West Coast in the Indian Peninsular. However, for real estimate, the aquifer parameters have to be taken into consideration. The above estimate may be considered as the minimum. Thermal discharges at Pyuga and Chumathang were measured in the month of March 2004. The measured discharge from a single borehole is 30 to 40 ls at Pyuga and 15 ls at Chumathang. In Pyuga Valley, covering an area of about 10 to 15 square kilometers, there are more than 10 such discharge points. If this is taken into consideration with the surface temperature of 95 degrees Celsius, the geothermal potential amounts to approximately 5,000 megawatts. If the cumulative discharges are considered, then the potential would be much higher than that reported. It has already been estimated that the Tattapani geothermal field has potential of 1 megawatt. Besides power, the Himalayan geothermal energy resources are best suited to support food industries. The lower and middle Himalayan regions experience varied agroclimatic conditions suitable for growing different varieties of fruits like apple, pear, peach, plum, almond, walnut, citrus, mango, raisin, grapes, etc. The total area under fruit cultivation in Himachal Pradesh alone is about 2000 km square with annual production of about 5,000 megatons of all kinds of fruits. With an annual growth rate of greater than 15%, the food processing industries have created investment opportunity worth $30 billion MFP 2001. By using geothermal energy, India can become one of the world leaders in value-added food products. Prospects of geothermal energy in India. India has a huge potential to become a leading contributor in generating eco-friendly and cost-effective geothermal power. Around 6.5% of electricity generation in the world would be done with the help of geothermal energy, and India would have to play a bigger role in the coming years in this direction. But the power generation through geothermal resources is still in nascent stages in India. Geological Survey of India has identified about 340 geothermal hot springs in the country. Most of them are in the low surface temperature range from 37 degrees Celsius to 90 degrees Celsius, which is suitable for direct heat applications. These springs are grouped into 7 geothermal provinces, that is Himalayan, Pyuga Chumathang, Sahara Valley, Cambay Basin, Son Narmada Tapi Lineament Belt, West Coast, Godavari Basin and Mahanadi Basin. Some of the prominent geothermal resources include Pyuga Valley and Chumathang in Jammu and Kashmir, Manikaran in Himachal Pradesh, Jalgaon in Maharashtra and Tapovan in Uttarakhand. A new location of geothermal power energy has also been found in Tattapani in Chhattisgarh. In addition, Gujarat is set to tap geothermal electricity through resources which are available in Cambay between Narmada and Tapi river. Future development and installations. A systematic geothermal survey in India began in 1973 undertaken by Geological Survey of India, and the existence of 340 potential sites was reported. 11 geothermal prospective districts have been identified till date. Most of them appear to have resources at temperatures of about 100 to 1200 degrees Celsius, but some appear to have reservoirs at 1 to 3 km depth with calculated geothermal temperatures of 200 to 2500 degrees Celsius. The most promising geothermal fields as on date are Northwest Himalayas, Pyuga Chumatung, Ladakh district, Jammu and Kashmir, where a 1 megawatt plant is planned, and Parbati Valley with the Manikaran field in Himachal Pradesh, wherein 1992 a 5 kilowatt geothermal binary cycle plant was successfully run. Central India, Tattapani region, Chhattisgarh, where the installation of a 20 megawatt binary plant has been planned. Plans to build India's first geothermal power plants are underway. Indian states Gujarat, Chhattisgarh, Andhra Pradesh and West Bengal are the first of many to announce interest in developing the BRIC country's first geothermal energy plant with power capacity in the range of 3 megawatts to 5 megawatts. The Ministry of New and Renewable Energy of India (MNRE) plans to set up a geothermal energy policy later this year to guide future projects. India is said to have a geothermal potential of 10,000 megawatts according to India Energy Portal. The Tattapani geothermal field is the most promising geothermal resource in central India, the government has said. Work to assess geothermal resource in Tattapani has been carried out over the last 30 years, and as per reports, very soon the first geothermal power project for India will be established in Tattapani, Chhattisgarh. Advantages and disadvantages of geothermal energy. Advantages. The first advantage of using geothermal heat to power a power station is that, unlike most power stations, a geothermal system does not create any pollution. It may once in a while release some gases from deep down inside the earth that may be slightly harmful, but these can be contained quite easily. Geothermal power plants have sulfur emissions rates that average only a few % of those from fossil fuel alternatives. The newest generation of geothermal power plants emits only approximately 135 grams of carbon as carbon dioxide per megawatt hour (MWHR) of electricity generated. This figure compares with 128 kg per megawatt hour of carbon for a plant operating on natural gas, that is methane, and 225 kg per megawatt hour of carbon for a plant using bituminous coal. Nitrogen oxide emissions are much lower in geothermal power plants than in fossil power plants. Nitrogen oxides combine with hydrocarbon vapors in the atmosphere to produce ground level ozone, a gas that causes adverse health effects and crop losses as well as smog. The cost of the land to build a geothermal plant on is usually less expensive than if you were planning to construct an oil, gas, coal or a nuclear power plant. The main reason for this island space, as geothermal plants take up very little room, so you don't need to purchase a larger area of land. Another factor that comes into this is that because geothermal energy is very clean, you may receive tax cuts and or no environmental bills or quotas to comply with the country's carbon emission scheme, if they have one. No fuel is used to generate the power, which in return means the running costs for the plants are very low, as there are no costs for purchasing, transporting or cleaning up of fuels you may consider purchasing to generate the power. The overall financial aspect of these plants is outstanding. You only need to provide power to the water pumps, which can be generated by the power plant itself anyway. Because they are modular, they can be transported conveniently to any site. Both baseline and peaking power can be generated. Construction time can be as little as 6 months for plants in the range of 0.5 to 10 megawatts and as little as 2 years for clusters of plants totaling 250 megawatts or more. Disadvantages. Fluids drawn from the deep earth carry a mixture of gases, notably carbon dioxide (CO2), hydrogen sulfide (H2S), methane (CH4) and ammonia (NH3). These pollutants contribute to global warming, acid rain and noxious smells if released. Existing geothermal electric plants emit an average of 122 kilograms, that is 269 pounds of carbon dioxide per megawatt hour of electricity, a small fraction of the emission intensity of conventional fossil fuel plants. Plants that experience high levels of acids and volatile chemicals are usually equipped with emission control systems to reduce the exhaust. In addition to dissolved gases, hot water from geothermal sources may hold in solution trace amounts of toxic chemicals such as mercury, arsenic, boron and antimony. These chemicals precipitate as the water cools and can cause environmental damage if released. The modern practice of injecting cooled geothermal fluids back into the earth to stimulate production has the side benefit of reducing this environmental risk. Plant construction can adversely affect land stability. Subsidence has occurred in the Warakai field in New Zealand and in Stoffen in Breisgau, Germany. Enhanced geothermal systems can trigger earthquakes as part of hydraulic fracturing. The project in Basel, Switzerland was suspended because more than 10,000 seismic events measuring up to 3.4 on the Richter scale occurred over the first 6 days of water injection.